In this video, we are going to go over how to configure a random vibration analysis with MSC Nastran. So by the end of the video, we're going to have this, where we are going to see the result of this random analysis. We're going to look at values like the power spectral density function values. We're going to look at the root mean square, also the number of zero crossings for displacements and strains and some of the elements that we use. Now, today, the example we are working with is from this paper, Random Vibration Analysis Theory for MSC Nastran. Now, this is a great paper because of the following. I really like textbooks or papers that give you worked out examples by hand. So if you look at example B, they actually go through the hand calculations of generating these values, the cumulative root mean square or the number of zero crossings and so on and so on. They actually work those examples by hand in this paper, which I really like. So I think that's a great way of learning. If you can see how the hand calculations are done, this will help you a lot in learning what the process is like. So the example we're working with would be this one, example B. I'm not really going to go into the paper itself. There you could go ahead and read it on your own time. I'm going to talk about the exact steps that you need to take in MSC Nastran to go ahead and configure the random analysis. So here is what we have. On the left is the current configuration of the Nastran model. It's configured for a linear statics analysis. We've already gone ahead and defined the boundary conditions and the loads, if you will. In this case, I think we're working with enforced displacements for the loads. Here's a summary of all the bulk data entries that we have. Now, to configure a random analysis, this is what you need. At the minimum, you need a few things. Number one, you need a RANDPS entry. This is going to be your so-called random loading, if you will. Technically, it's the PSDF. You're going to need a table entry for that, table RAND1, I believe it's called, and then you're going to need to create a case control command called random. Now, at the minimum, this is what you would do to configure a vibration analysis. But here, since we're starting off with the linear statics analysis, we have to add a few additional things. We have to create what's called an RLOAD1, so this is going to be your dynamic loading, if you will. We have to specify how to extract the eigenvalues, so we have to create an eigenvalue entry for that. And then we have to configure what frequencies to perform the frequency response analysis for. So I believe we need to define the frequency entry for that. So here we're going to configure a SOL108 for the direct frequency response analysis. So this is our first part of the video. And then we're going to configure a random analysis with these bulk data entries and case control command. Here in this other text editor, I have a more exact explanation of what we're doing. So if before, here on the left, we have these entries, here on the right are the new set of entries. So again, we're going to define one entry to specify how to extract the eigenvalues, another entry that specifies which forcing frequencies are used for the frequency response analysis, one RANDPS entry that specifies your random loading, if you will, RLOAD1 entry that specifies the dynamic load, and then a table entry that helps define the so-called GF term in the random loading. And then here are some more details regarding how do we configure the case control commands. Now, I'm going to walk you through the steps that you need. I'm really not going to discuss sort of the theory and all that because there's already a good paper on that. There's already documentation all over the internet on that. So I'm not going to take your time going through every line in the papers, the textbooks, and the user's guide. This is more of all the steps I need to define all of this. Okay, so again, I am assuming that you have already configured a statics analysis. So let me show you what that bulk data file looks like. So here on the right is what that file looks like. And here, let's go ahead and drag it. So here everything I need to define those nodes. And here, let me bring up this diagram here. So this would be example 8, right? So here, if you look at this diagram, there are 1, 2, 3, 4 nodes. There's a C-bush element representing the spring between all the nodes. Here in green are going to be concentrated masses. The nodes at the left and right, those are going to be fixed, but we're going to have enforced displacements at either node. I think we have 2 load cases to consider in this scenario. I think this example actually is considering only 1 load case. The load case is where you have an enforced displacement at this one node and the other node is going to be fixed. So we're only dealing with 1 load case in this example. I think in a future tutorial, I'll consider multiple load cases just so you see what that process is like. Okay, so let's take this bulk data file and let's go ahead and use the tool we are using today. So today we're using the Sol200 web app. So that would be this web application that you see here. We're going to jump over to the viewer and let's talk about units. So at the very top, it's not required, but it's nice to do. Specify what your units are. It's very easy that you go through an example and you never think about what the units are. So here, the units we're using are meters, kilograms, and newtons, and then seconds for time. So whenever we look at the results, that's where we're dealing with. So let's go ahead and take that bulk data file and upload it to the viewer. So here, if you want, you could jump to the fem label tool. First, let's go ahead and mark those checkboxes. Let's recolor this. And let's zoom in. So here, let's go ahead and use the fem label tool. Let's go ahead and pick the 2 concentrated masses. So here we have concentrated mass 4 and concentrated mass 5. Let's go ahead and pick C-bush 1, C-bush 2, and then C-bush 3. And then let's go ahead and turn on the nodes. So this is what the model looks like. From this node to this node, you can imagine there's a spring represented with the C-bush element. Then here, there's another spring with another C-bush element, then a third spring. And here in yellow are going to be the so-called concentrated masses. What do the loads look like? So let's go ahead and jump out of here. Let's open the loads display panel. Here, let's go ahead and increase the size of the arrows. So let's go ahead and use maybe 1. And so like I said, they're fixing both nodes and then they're adding an enforced displacement at either end of this system, if you will. Here, like I said, we're only considering 1 load case. So we're only considering this enforced displacement. You'll notice that here, like the paper discusses, so again, that would be this paper. They use unit values for the loads. Here, they're using a unit enforced displacement for this displacement that you see here on the far left-hand corner. Okay, so now, like I said, this is currently configured for Sol 101. So we go here and we'll look at this section here. It's currently set to Sol 101 statics. Now, for most of you, you're going to be selecting modal frequency response analysis, but the paper uses direct frequency response analysis, so we'll go ahead and use Sol 108. Now, we need a few things to define now, so this is where I bring up a text editor. We need to define these 2 entries, the eigenvalue entry that decides how to extract the eigenvalues, and then the frequency entry that decides at what forcing frequencies do you want to perform the analysis for. So let's go ahead and configure those right now. So let's go ahead and go to the bulk data section. Let's go ahead and reset table here on the far right hand corner. Let's go ahead and look for the eigenvalues entry here, eigenvalue RL. Let's go ahead and click open, click create entry. And now let's go ahead and display the description. So I'm looking for the number of roots desired. Here, since I believe we should have anywhere from 2 to 4 natural frequencies, but here I'm going to only specify extract at most 10 natural frequencies. Here, if I click on this arrow button here in the top right hand corner, I get a preview of what that bulk data entry looks like. Now what we do, we jump to the case control section, we go to commands, we have to tell the head of the file, hey, use that eigenvalue method we just defined. So we'll go ahead and search for the method command. We'll turn it on for the above subcase level. You notice that now here on the right, we have a method command visible. And now let's go to configure. Let's go ahead and select that eigenvalue entry we created a moment ago. Great. So now this is configured to use that eigenvalue method to extract at most 10 natural frequencies. Now, at what frequencies, at what forcing frequencies are we going to perform this analysis for? So now we have to go ahead and find what's called a frequency entry. So let's go ahead and look for frequency here on the left. And you have a few options here, frequency 1, 2, 3, 4. Here we're using, I believe frequency. Or no, I actually forgot what they're using. I think it may have been, here, let me just double check just to be sure. So here, I'm looking at the one example they already did for us in the paper. So let me bring that here. So here they are using frequency 1. They are doing, here, let me make sure this is right. A 1 and 2. This might be off. Let me look at the paper. Because in the paper they tell us exactly, or actually, oh yeah, this would tell us. Okay, so they do this for 2, 4, 6, 8, and 10 hertz. So let me see which entry that was. I can't remember if it was frequency 4. Nope, that wasn't it. Frequency 3. Or maybe it was frequency. Oh, right. I guess it was frequency 1. So this is where I manually supply the natural frequencies that I want. Now, when you come here, be very careful with the values they specify. Right now, I've supplied only integers or numbers without decimal points. This is going to cause an error with Nastran. I have to manually specify that these are real values, so I have to manually type out the decimal points. So let's go ahead and type those in. So 2 hertz, 2.0 hertz, 4.0 hertz, 6.0 hertz, 8.0 hertz, and 10.0 hertz. Here's the respective frequency entry, if you will. So now we have to go back to the case control section. We have to go ahead and tell Nastran, hey, these are the forcing frequencies that I want. So here we'll go ahead and turn on the frequency command for the above subcase level. We'll go to frequency and we'll select that frequency entry we configured a moment ago. Okay, now let's go ahead and see where we're at with our agenda, if you will. So I've defined the eigenvalue entry. I defined the frequency entry. I've defined the method command. I've defined the frequency command. Now we need the dynamic load. So now we have to define what's called an RLOAD entry, which would be this row, if you will. So let's go ahead and do that. So for this, let's go to the bulk data section, select entry, and look for RLOAD1. And let's go ahead and create another entry here. Let's go ahead and select that enforce displacement we saw earlier in the video. And then I believe they only use the value of 1 here for this term. So here, let's go ahead and look at this. Here with the lower and upper bound, we know we're analyzing this from 2 hertz to 10 hertz. So maybe we'll go ahead and go from 1 to 5 hertz. And here you'll see that it's from 1 to 5 hertz. So this is what this component of the RLOAD1 entry will look like. And like I said before, if you ever want to look at the preview, this is what that will look like. And here, let me look at my notes just to make sure that's what we want. Okay, so I see from my notes, they also defined another term. I don't expect this term to really change the dynamic load. They use a value of 0.0 for the TDRD term. Okay, that really didn't matter. And here, since we're using an SPD entry, we have to specify the type. If you're loading with something else, if it was maybe force or pressure, you would use load. Or since it's the default, you could just leave it blank. But here, since we're using the SPCD entries, since we have enforced displacements, we have to manually specify, is this a displacement, velocity, or acceleration? Here it's a displacement, so we'll select the disp option. Okay, so I believe we're done with the RLOAD entry. Now we have to go back to the case control section, and we have to tell it, hey, this is where I'm going to perform this analysis. And here, let me show you how you would do this for a second loading, if you will. Here, we'll go ahead and create another entry, and we'll say do this for the second enforced displacement, and we'll go ahead and use the same values for these columns. And then for the type, we'll go ahead and select displacement. And then this is what the temporal part of the dynamic load looks like. This plot here is not considering the load. If it was a pressure load, it wouldn't be considering that pressure load yet. We're only considering the temporal part of the dynamic load. So that's what that temporal part of the dynamic load looks like. Okay, now let's go ahead and assign these dynamic loads to subcases. So here we'll go to case control commands, loads and BCs. We'll go to this row, DLOAD. We'll click that. So the first dynamic load for the first enforced displacement, we'll assign it to subcase 1. And then the second dynamic load, we'll go ahead and assign it to subcase 2. So now if we look at our list of to-dos, we've defined the RLOAD entry, and then we've defined the DLOAD entry just now. If you look at the output here on the right, you can see that we have a new DLOAD entries defined here. So this is the dynamic load 1 and dynamic load 2 that we defined a few moments ago. Now, I believe we're ready to perform our frequency response analysis. So here, you can click on the inspect button just to see if there are any errors. As any FEA procedure would go, you would always have errors. Here, let me show you one example maybe of an error we might have here. Let me purposely forget to define the load here. So here before we had it selected to the enforced displacement, but here it's blank now. If I click on inspect here, I should get an error saying, hey, there's an error with this, and yeah, we do. So here you notice that there's a red message saying you have a user fatal message. If you scroll down, we highlight what the error is. It says that excite ID is required but was not supplied, and that was my mistake. That's okay. Let's go back there. Let's go ahead and select that enforced displacement. Click inspect again, and we should have resolved the error. Now, once you're done, and you see here it's complete with no error, now we can go to download. Here, let's go ahead and click this button here, add HDF5 out. This is going to output the H5 file, H5 that contains the results. Here we'll say upload the PDF and immediately run the frequency response analysis. Okay, so we're done. Normally what you would be looking at is the F06 file. So here are some examples of what those results look like. I believe we want to look at this for... Oh, I don't like this output right now. Right. So you notice that the format of the output right now is not in a format I personally like. Right now it's outputting the result, all the results for forcing frequency 10. And then here goes row. These are the results for node 1, node 2, node 3, 4, and 5. I don't like this format, so let's go ahead and change that format a little. So we'll go ahead and go back to the case control section, commands, and configure. If you go to displacement, you can use the sort to option. And what I'll do right now, let me copy this actually. Let me copy this so we could look at it later. So again, I've used the sort to option, and now I go to download and upload PDF and run again. And we'll go ahead and give that a moment. And then we'll go to results in the F06, and then we'll go ahead and copy this. So here on the left is the previous format using the default sort option. So you see that here, all of these results here are for forcing frequency 10 Hertz. and then each row is one node, node 1, 2, 3, and 4. I really don't like this format. I like using the sort to format. So here what we have now, all of these results are for one node, node 3. So point ID equals 3. And now each row represents a different forcing frequency, 2 Hertz, 4 Hertz, 6 Hertz, 8 Hertz, and 10 Hertz. I like this format more than the default format that you saw here on the left. Okay, so let's go ahead and do confirmation here. Let me see if I can look at, okay, let's do this. Let's download the F06 file for this example. And let's go ahead and see if I can open it here. So let's go ahead and open this in Notepad. And what I want to look at are the complex displacements for node 2 for the first dynamic load. So that would be here, because the paper gives us the values that we should be expecting for that. So let me look here. Oh, I'm looking at node 1. So my mistake, I was looking at node 2. I was looking at node 1. So if you recall, the dynamic loading, if you will, for node 1 is just a constant. So if we look back here, and the load is, the enforced displacement is the unit load. So if we look back here, and if we look at our load entry, the temporal part is basically 1 here. That would be the blue line for the real term. The enforced displacement also has a value of 1. It's a unit enforced displacement. So the product of the unit displacement and the temporal part, which is 1, gives you a value of 1. So then when we look at the results for node 1, remember at node 1, that's where we have the unit enforced displacement, and that's where we have the dynamic load. The term for component 1, that's all 1. So you see 1, 1, 1, 1, and 1. And this would align with what's shown in the table. So here it's the same data. So just to prove to you we're following what was shown in the paper. Okay, now I believe, oh, right. So we also want the strains in the spring elements. In this case, we're using C-bush elements. How do we output the strains? So to do that, you go to the case control section and you go to command select and you look for the strain command. Let's go ahead and turn that on for the above subcase level. Go to configure, and then maybe we should also use the sort to option, just because we didn't like the original way of listing the displacements. And here we'll go ahead and rerun this. And then if we're lucky, in the F06 output, oh, I guess not. Let's go ahead and download the new BDF, F06 file, sorry. So let's go ahead and open that. And now if we look in this example, let's go ahead and look at the complex strains. Let's go ahead and see if I can find that. For element 2. Okay, perfect. So here are going to be the complex strains in the second spring, or the second C-bush element. So if you look here, that would be this table on page 17. So on page 17, they give you what the expected output is for the strains in the spring elements. You can see it's at negative 6.7 or negative 0.679, and then at the end it's at negative or positive 0.02645. You can see that's the same value that we have in this example. Now, some of you might be asking, okay, that's cool that you're showing me a text file, but I actually want to create some plots. Here, if you look at this table, if you look at this row, H5, here on the far right-hand side, you have this column result files link. You could click on the HDF file explorer. This is going to open the H5 file, and it's going to automatically create the plots for you. So here, in this case, it's creating plots for the complex strains. And right now, I only want to look at element 2 for subcase 1. So the same values that you see here, they're going to be shown here in the plot. So right now, let me make sure we're looking at this. Right now we're looking at the so-called, here, let me turn on the peaks actually. Right now we're looking at the strain in the axial direction, if you will. Or no. We're looking at the strain in the X element coordinate system. So it would be here. So here, let's go ahead and select TXR. So the R represents the real component. And here it's telling us it's a 0.2703. And if you go back to the text editor, you look at 4 hertz, it is 0.02703. Now, what's the imaginary term? Here it's 0.137. So if we wanted to, we can go ahead and select TXI. And let's go ahead and select element 2, subcase 1. Let's go ahead and turn on the peaks. And here we get the same value, 0.1372. Also, if you wanted to, you could do this for displacements, create plot. And now we're looking at the same values that we had a moment ago. So now if instead of the strains, I wanted to look at the complex displacement vectors that you see here, you would go ahead and let's maybe do this for load case 1. So let's show 0.1. So here, if you look at this column, let's go ahead and pick this one. So here it's 1 as expected. Now, what about 2 maybe? Here you can see there's some variability in that node or degree of freedom. That's because we really didn't. It was a free node, if you will. And then for node 4, I believe that node was fixed. So I don't know if that's going to show up here. So let's go ahead and maybe go to -1 and then 1 here. Oh, interesting. We don't get, I don't expect there to be values for that, but let's see. Oh, right. So here, if you look at this table, all the values are 0 for node 4. That's because that node, if you recall, this far node was fixed. So this was our node 4 here on the far right. So all of those values should be 0, which they are. I believe it's even visible in the results. So here, let's go and go to 4. Right. So if you look at this table, for component 1, the real term, all of the values are 0. So the real values would be this value, this value, this value, this value, and this value. The imaginary terms would be in the second row. So here, imaginary, 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 and so on and so on. Okay, so far we've configured our frequency response analysis. Now we're ready to move on to the random analysis. So what do we have to configure there? First, we have to configure a table entry that defines the GF term for the random loading. So you might be asking yourself, okay, what's the random G loading? Let me go ahead and do this. Let's go ahead and open the quick reference guide. And let's go ahead and look at the RANDPS entry. So right now we needed to find this term here. How is G going to vary for those forcing frequencies, 2 hertz, 4 hertz, 6, 8, and 10 hertz? So to define G of F, you could just define a constant, or you could define a table. And here we are going to be using a table. So actually, let me go ahead and look at my notes. I forget what values they used for the table. So they go here, let's go ahead and build this out in the web app. So we'll go back to the pre-web app. We'll go to the bulk data section. We'll select entry, reset table, and search for TABRND1. We'll create an entry here. We'll create or add 2 rows. And then we are going from, let's see, 0.1 hertz to, let's go ahead and see, 10 hertz, and they just use a constant line of 1. So this is our G term here on the right, and one funny thing about this plotter, sometimes you use a constant value, it kind of shows you this. But what's happening, you're zoomed in very closely, that's what's going on. So what you can do is this. You can hover here, and you can actually change the value of the vertical axis. So we'll go and move this from 0 to 2 on the vertical axis. So now you see it was actually a flat line this whole time, but what happens is that you're zoomed in so close that it's kind of deceiving you a little. So just keep that in mind. What you can do is you can just manually modify the vertical axis bounds, and then that will show you the flat line. So this is G of F. Now what we can do is we can go ahead and look for that RANDPS entry and create the random loading, if you will. Now this J and K, let's go ahead and look here. Let's go back. Let me do this. Let me try to explain what's going on here. So what we're going to do now, we're going to do this. So here on the left is the actual expression for the random loading. So here what we're going to do is we're going to say J and K. So J and K, that's going to be equal to subcase 1 and subcase 1. So for J and K, we're going to be using 1. So here we'll go ahead and select subcase 1 and subcase 1. Now, one thing to keep in mind, whenever you're new to one of these bulk data entries, it's important that you read the remarks. The remarks are going to tell you how do you use that entry. Here, since we set J equal to K, since we're saying do this for subcase 1, 1 equals 1. So here it tells us that X must be greater than 0 and Y must be equal to 0. So what do X and Y define? X and Y define the constants for the real and the imaginary values here. So what we're going to do is we're going to set X to maybe 1. In the paper they use 5, but because the remarks say that since J and K are both 1, since we're doing this for subcase 1 and subcase 1, Y must be 0. So here in the X and Y column, I'm going to say use 5 and use 0. And then for the GF term, so that would be this one, we say use that table entry that defines the GF term. So remember, the GF term is going to be defined for every forcing frequency. So here you ask yourself, okay, what is GF for 5 hertz? For 5 hertz, it's going to be 1. What if it's 2 hertz? What is GF going to be? It's going to be 1 hertz. So here it's a flat line. Okay, now let me do this. Let me make sure I'm following my notes here. I want to make sure I define this random loading properly. So let's go ahead and look for the random loading, which was a RANDPS entry. It moves to the side. Let me make sure I'm following. So I get the J and K terms are both 1 for subcase 1. The X term is 5. The Y term is 0 for the imaginary component. And then we're pointing to the table entry. Now, I believe we're almost done with this. What else is there to do? So we defined the table entry. We defined the RANDPS entry in this row and this row. Now we need to define what's called the random command. So now we go to the case control section. Here in this navigation bar, here on the right, we have subcase combinations, fatigue, and random. You want to click on random. And we'll go ahead and select that random loading we defined. We'll say assign it to the above subcase level. So if you look at the new head, the random command is above all the subcase blocks. That's what you want. We said perform the random analysis for that one random loading we defined a moment ago. Now let's go ahead and click inspect. We'll see if that's successful. Here we're done with random. We did define displacement and strain. And great. Now we see that it's been successful. The inspection is good to go. So now we can go ahead and try and run Nastran, and we'll go ahead and see what the results are. So if I look at the results, or the paper rather, they want us to look at the cumulative root mean square, the power spectral density function values for the strains and the spring elements, and they want us to look at the number of crossings. So let's look at this first one. I believe this was for element 2. Right, I'm assuming all of this is for element 2, so let's go ahead and go to results. And let's go ahead and download the F06 file. Let's go ahead and open this in the text editor. And let's look at the first table. So right now, let's go ahead and hunt for this table here, the cumulative root mean square for the strains and the spring elements. So let's go ahead and scroll and scroll. And this would be this table here. Let me make sure. So here we have the complex strains, but right now this is for the complex values, real and imaginary terms. What we want are the root mean square. Oh, and I forgot to output the data. So you want to output the the cumulative root mean square, the power spectral density function values. How do you do that? If you go to case control commands, go to commands and configure. For displacement, select this. Select R all. So what R all is going to do is going to output the PSDF values, the I forgot what these autocorrelation values, and the CRMS values. So you could either select PSDF, ATOC, CRMS, or you can just select R all for both the displacement and the strain. So let's go ahead and select strain, R all for the strain. Now, when you use the select box, be careful. If you just click on the mouse, that's going to deselect your previous selection. So here, hold the control key, and then you can select multiple options here. So control, hold down the control key, then use that to select multiple options. Now, if you look at the output, you notice that the R all keyword is on for both displacement and strain. So now if I run this, I'll get those values of number of zero crossings, cumulative RMS. And here, let me go back to the pre-web app and then go to the F06. Okay, so here we can look at the table here. Or actually, let me just download the F06 file. So now I should get, right, so here you can see we get PSD function values. Now what I'm looking for are the cumulative root mean square. Okay, so I get that for the displacements. I'm looking for the strains and the bush elements. So here we get the PSDF values for element 1, 2, 3, and 4. But here I just want the values for element 2. Oh, these are the PSDF. I want the CRMS values. Okay, so they'll be here. Okay, so this is the table we're looking for. Now, if you look at the paper, this is that same table, 0, 1.67, 1.82, and so on and so on. You notice those are the same values that we have here. Great. So that means we're following the example that was provided in the paper. Now, after CRMS, we need to look at the PSDF values. So that is a little further up. So here you can see PSDF. Here's table 2. You can see the values are 2.35, 0.459, 0.449, 0.125. No, sorry, this is a 0.0449. Keep in mind the exponent here. 0.0125 and 0.00522. That would be the same values that you have in this table. And now for the last table, they want the number of zero crossings for element 2. So here, you could just scroll and look through this, or you can just search for that table. So number of zero crossings. So here, you can see for element 2, it's a 3.345. And that would be the same value that's shown in the table. Okay, now we looked at the tables. How do you create plots for these? You can come here and let's go ahead and look at this. Let me rerun this. when you run Nastran, it will give you a link to the H5 file. So if we look here, it seems like it's not compliant in this example. So let me do this. Let me download the H5 file. Let me go ahead and actually open it here. So let's say you run this on your own desktop. You can just download that H5 file and then upload it to the H5 file. Or sorry, let's say you ran this analysis on your own desktop. What you can do is upload the H5 file to this web app and you can create your plots. So here, let's go ahead and look at the same values. So the number of zero crossings, the PSDF, and the CRMS values, they're contained in this data set. Strain bush and nodal displacement. So here, if we look at the strain bush, let's go ahead and create a plot. And here there's going to be a lot of data. So maybe let's do this. Let's go ahead and only query the data set for element 2. And let's go ahead and create the plot. And now we have a few things here. This first plot is going to end with RANDOM1. This is going to be your PSDF value. So if we look here in the paper, we should get 2.35, which I believe would be the highest term. So here, if we hover over this, right, we get 2.35, and then we get 0.459. So right, the second row would be 0.459. The next value, it ends with RANDOM3. This would be the, I believe, the cumulative RMS value. So here it's 1.84. So let's go ahead and see if we can find it. Or that might actually be the RMS term. Right, so let's go ahead and look in here. There is a table for the RMS value. So that was not the cumulative root mean square. That value was actually the root mean square for element 2. So here it's a 1.84. So let me go back here. 1.84. The next value, which would be this green point, if you will, that's a 3.34529. That's going to be the number of zero crossings. So if we go and scroll here, or actually here. So here we're at the table for number of zero crossings. If you look at this row for element 2, the number of zero crossings is at 0. For the strain along the Y, oh sorry, here you can see it's 3.34 if you're going along the x-axis of the spring element. So that would be this 3.34 here. Now the last one, this is the cumulative root mean square. So if we look here, let's look at what's going on at 10 hertz. At 10 hertz, we have a value of about 1.84. So let's confirm this. Let's go ahead and look for the cumulative root mean square. This is going to be for element 1 and element 2. At 10 hertz, it is 1.84, and that's aligning with what we see here in the plot. Okay, so I believe we went over everything that was discussed in the paper. There's one last thing I want to demonstrate. If you have a million nodes, that's going to be a lot of data in the F06 file and a lot of data in the H5 file. Maybe it's 10 gigabytes, maybe it's 50 gigabytes large. How do you reduce the size of the result files? So here what you can do is say, you know what, I don't want data for all 4 nodes in the model. I only want data for node, node 1 and element 2. So how do we do this? If you go back to the viewer, you can go to the case control section, command, or actually you can go to the bulk data section. You can define what are called set commands. So here we'll look for set. We'll open that. We'll create 2. Here, let me move this to the side a little. Let's go ahead and fit the model. Let me do this. Let me click on this pick icon. For the first set command, I'll say, you know what, let's just pick node 1. And you notice that now set 1 has 1 here. And for the second set command, let's go ahead and pick element 2. So we'll go and select this one. I believe I have to pick this one. Here, alternatively, you can just manually type in the element ID, and that's the same thing. You can either pick or type in the element ID. Okay, now let's go ahead and do this. So if you look here, this first set command is pointing to node 1. The second set command is pointing to element 2. So what I can do now in the case control section, I can say for the displacements, instead of getting all the displacements for all nodes, I say, you know what, only get the displacements for node 1. And then for the strain command, I'll say get only the strains for element 2. So instead of getting 10 or 50 gigabytes of data, so responses for every node, I'm saying, you know what, get displacements and strains for node 1 and element 2. So now if I click run, you'll see that the F06 file is going to be smaller. So let's go and maybe download that in a moment. So let's go to here. Let's go ahead and download the F06 file. Let's open the F06 file. So remember, before we got displacements for nodes 1, 2, and so on. Oh, here I'm getting... Oh, right. So here let me step back a moment. Before we were getting displacements for nodes 1, 2, 3, and 4. But now I'm only getting displacements for node 1. Now, what about the elements? Before we were getting displacements for elements 1, 2, and 3. But now I'm only getting strains, for element 2. So here you can see element 2, element 2. There is no element 3 or element 1. It's only element 2. So that's a way to reduce the amount of data. And then when you look at the plots, let's go ahead and maybe open the HDF5 Explorer. Since we said only get data for node 1 and element 2, if you try and get data for maybe some other node, node 4 or 3, here, let's go ahead and do that. So for the complex displacement, say you want data for element 2. It's going to give you an error because, hey, you didn't output data for node 2 to the result file. So there is no data for result 2. That's why you get the error. Same for node 3. Let's go ahead and run that. Node 3, get an error. But, hey, once I say get data for node 1, there's data for node 1. And same thing for element 2. You want data for element 2, you get data. But any other element like element 1 or 3, you get no data because you didn't tell Nastran to output data for those elements. Okay, so we're pretty much at the end of the video. Let's quickly recap. So here on the left is what we started off with. So we started off with a very simple statics analysis. But then here on the right, what we did is we added a few additional entries. First, we configured a frequency response analysis. So to do that, we defined the EIGRL entry, the frequency entry, and then we defined the frequency command, the method command, and we defined the dynamic loading, so the RLoad1 entry, and then we defined a DLOAD command. So that was enough to configure the frequency response analysis. Then, to configure the random analysis, we have to define a few additional entries. We had to define the table TABRND1 entry and the RANDPS entry to define a random loading. And then we defined the random command. Just those few things, the table, the dynamic loading, and the random command, that's enough to start you off with the random analysis. And then we output the displacements and the strains. We looked at the data in the F06 file. And then we went ahead and looked at the same data in some plots, like we discussed earlier in the video. And this is all from this paper. Let me go ahead and show you the paper before we close for today. So this was a great paper, Random Vibration Analysis Theory for MSC Nastran. Again, we followed example B that's provided in this exercise. So that would be example B, storing results with 2 sensors and 1 actuator. So again, I think this is a great paper because it shows you hand calculations for all of these different terms, so you can actually follow the math. I think this is honestly the best way of learning. If you show me how to do this by hand, this will help me a lot in understanding what all these different terms are, and that's what the author did for us in his paper. Okay, so that's pretty much the end of this tutorial. Oh, and one last thing, just in case you want to, if you want to use the pre-web app, all the web apps that you saw today, you can visit theengineeringlab.com. If you come here in the top right hand corner, you would click on free trial pre-post web app, fill out the form, and you would get access to all of these tools so you can go ahead and practice how to configure a random analysis with MSC Nastran. Okay, so as always, thank you for watching, and we're pretty much done for today.